So projectile motion and collisions should have made you pretty good at splitting muzzle velocities and trajectory velocities into their horizontal and vertical components. We're going to try some stuff on ramps, which uses the same technique, but instead of harmonizing speeds onto horizontal and vertical axes, instead we're going to convert forces that are vertical or horizontal into off-angle reference frames. Now that sounds like a lot of words, but if I can just draw you to this simple example up here. I have a 5 kilogram block sitting on a triangular shaped wedge. For the moment, we're going to have no friction on this. Okay, so I don't have to worry about it sticking. So if you can sort of imagine what that would be like in a universe with no friction, you put a block on a ramp, there's nothing holding it there, it's going to slide down the ramp. Obviously, that's how that works. It's like you being on a hill in roller skates, or worse, a frozen hill on ice skates. Down you go. So why does it do that? Well, like all objects on the surface of the Earth, this thing is experiencing some gravity. And the thing about gravity is gravity pulls straight down. That's your force of gravity right there. And we can calculate that by doing mass times the gravitational acceleration. So for this particular block, it would be 5 times 9.8, which gives you 49 newtons. Okay, but here's the problem. That block can't move down. If it were to move straight down, it would have to crush its way through this triangular block, which it's not allowed to do. So we have this problem with the geometry here where the only force that's acting is acting in a direction where the object is forbidden from traveling. So what does it do then? And the idea is that I want to take this force, which is currently pointing in an inconvenient direction, and I want to write it in components that are inconvenient directions. For example, up or down the ramp. If I had a force component that was parallel to the surface of this triangle, then I would know whether the block was drifting up or drifting down, and I would know how many newtons of force were doing that. So I need to get this blue line split into two components so that at least one of those components is parallel with the surface. So if you think about how you did components before, you took your muzzle velocity and you broke it into a Vx and you broke it into a Vy. So if I take this whole diagram and I turn it until that arrow is pointing down like this, so this is now here, this Vx is now here, and this Vy is now here. So if that was your gravity pointing straight down, this Vx piece would be parallel to the ramp surface. This one, by definition then, must be perpendicular to the ramp surface. So I'm going to try and draw that onto this particular diagram. If gravity looks like that, then my force perpendicular to the ramp looks like this. And my force parallel to the ramp looks like this. And they meet at a 90-degree corner. Sure, that's not too bad. I'm at a bit of an angle, so my diagrams are a bit skewed sometimes. So if I can draw them on there, then I can maybe do some calculating to see how much of this 49 newtons worth of gravity are parallel to the ramp and how much of them are perpendicular. So I'm going to have to do a little bit of angle work here. So first off, if this is 40 and gravity meets the bottom at a 90-degree corner, then this up here, this must be 50. Because 40 plus 50 plus 90 adds to 180, and there are always 180 degrees worth of angles inside of a triangle. If this is 50, and this line is perpendicular to the surface of the ramp, that means there's 90 degrees worth of angle here, and I've already sucked up 50 degrees of them, so this angle here is also 40 degrees. So I'm going to take this triangle and I'm going to redraw it. Where am I going to redraw? I'll redraw it down here because I need some space for some calculations later. So I end up with my force of gravity that is perpendicular and my piece of gravity that is parallel, adding up to the total force of gravity, which is straight up and down and is 49 newtons. And I just used a little geometry logic to figure out that this thing was 40. This is 90 degrees by definition. This is the force perpendicular. And this is the force that's parallel. Okay. This is just a triangle now. It is off axis, right? We were used to doing them where this was horizontal and this was vertical, but the rotation of the triangle is irrelevant. I have the length of the hypotenuse, I have one angle, and I'm trying to find the thing that is opposite to that angle and the thing that is adjacent to that angle. So I should be able to do this reasonably easy. This thing, perpendicular force, if it is adjacent to the 40, then cosine 40 should be the perpendicular force over the hypotenuse. Therefore, the perpendicular force is equal to 49 cos 40. And the parallel force is opposite the 40 degrees. So opposite over hypotenuse is a sine. So sine 40 should be the parallel component over the full force of gravity. And so the parallel force then would be 49 sine 40. So if I actually work those out as numbers, hopefully my calculator is available and not being ridiculous today. Let's see. 49 times the cosine of 40 is 37.536. No, it's really not working. And the piece that is parallel would be 49 sine 40, 31.496, 39, which is 39.497 if I round it. Sorry for that awkward pause. Took me a minute to work the numbers out. This is not 39.497. It is 31.497. Okay. Now, the reason I had a scratch my head moment, you notice that this number, the tendency to slide, is less than the tendency to be pressed into the block. Now that's good. That makes sense, because this angle is less than 45. Once I get past 45 degrees, the thing becomes very steep. So the tendency to be pressed into the block should switch. This should be less than this, if the angle is more than 45. Okay, now if you take that to extreme ends, because this diagram, trying to get all the vectors arranged on it and decide where the 40 is relative to everything else, can be a little bit tricky to wrap your head around. The best way to do it, in my opinion, is to set this angle to 0 in your head. So let me draw that for you. Here's the bottom of the triangle, and here's the top of the triangle. And here's your 5 kilogram block. If that angle is 0, so I'm going to pop that in there, alpha equals 0. That's the force of gravity, and it's also the force that is perpendicular to the surface of the triangle, right? Because the triangle is flat, this thing is pressing right into that hypotenuse. This would only be true if you had a trig function attached to the gravity. You notice that that's happened. You've got a trig function attached to the gravity here. You need the trig function that's worth 1 when alpha is 0. So your choices are cosine and sine. And cosine looks like this, and sine looks like this. This function is worth 1 when alpha is 0. This function is worth 0 when alpha is 0. So this thing, this perpendicular force, has to equal the force of gravity when the thing is flat, which means that this force of gravity must have a cosine alpha attached to it. So you notice that happened up here, right? The perpendicular part had the cosine. The other extreme example is if I take that ramp and I make it not a ramp at all, I make it like this. So that alpha is 90 degrees. So there's my block. Now the perpendicular force would be pointing that way. The parallel force would be pointing that way. And you can see in this diagram, nothing is actually pushing in this direction. This is entirely gravity. And again, you're hunting for a trig function to attach to this gravity, because that's how you break things into components. You attach a sine or cos of the appropriate angle to it. I want the trig function that's worth 1 when alpha is 90. So at 90, cosine is worth 0, and sine has reached its peak. So this needs a sine on it. You notice that happened. The parallel part ended up with the sine function attached to it. So that said, now that I have a force component that's broken up, I can actually use that force component to do some calculations. So looking at this block, if there's no friction and only gravity, I've got this piece of the gravity perpendicular to the surface, and I have this piece that's parallel. So if I were to try and draw a free body diagram on this, there's my well, let me erase this then so that I have some clean space to draw. I have my force that's perpendicular to the surface of the ramp at 37.53 newtons. I have my force parallel to the ramp at 31.497 newtons. This block is sitting on an object which is pushing back to try and stop the thing from falling through it. And the force you need for that is called a normal force. And perhaps you remember that from grade 11. And normal forces are always perpendicular to the surface that the object is resting on. So there's a normal force there. If we had friction, it would be pulling backwards, resisting the slide, but we don't. I'm out of forces, so here's my diagram. From that, I can determine that my normal force has to be equal to 37.53 newtons. Otherwise, this 5 kilogram block would be crushing its way through the triangle. So that's one force figured out. This is 37.53, this is 37.53, so it's balanced. There is no drift in this direction. And you can sort of expect that, because blocks, when you set them on ramps, don't suddenly hop right for no reason. In this direction, the parallel direction, I have an unbalanced force. I have 31.497 newtons pulling down the ramp and nothing resisting it. So if I do that, a net force would end up being 31.497. It's the only force involved. And net forces always end up in net masses multiplied by net acceleration. You did this, I should have done it with masses on pulleys and strings in your grade 11 course. I of course know the net mass of this block, it's 5. Pop that in there. So 31.497 over 5 would be my net acceleration. So my A net is, let's see, 31.497 divided by 5 gives me 6.2993 meters per second squared. All right, so I know the size of all forces acting on that pink block. I know the net acceleration of that pink block, and I know that it happens to be 3 meters away from the tip of the ramp. So if I have an acceleration and I assume that that thing has an initial speed of 0, I should be able to calculate the time it takes to travel down that ramp using my kinematics equations. So the one that connects initial speed, time, distance, and acceleration is distance equals VIT plus 1/2 AT squared. So 3 meters, 0 initial speed multiplied by t plus 1/2 6.299 t squared. That would be 3 equals half of 6.299. Be 3.1 something 1499. 3.1496. So I'm going to round that up to 3.15. Yeah, 3.150 t squared. 3 divided by 3.150. 0.952. So t would be the square root of 0.952. T would be 0.976 seconds. All right, so net, I was able to take this block whose force was in an inconvenient orientation, and I was able to convert that force that pointed in a direction I couldn't use into directions I could use. The piece that is opposed by the block, so the perpendicular component, which is balanced by the normal force, and the piece that is parallel to the block, which is unopposed by anything. Once I had it broken down that way into those two pieces, I could find out the size of my normal force. I could find out the net acceleration on the block. Once I had the acceleration, I could solve some sort of time about it. So now I know everything about this system. But it did require me to break it into these non-standard coordinate directions first, the perpendicular to the surface and the parallel to the surface direction. So I'm going to erase this, and we're going to do one that has a hanging mass on it, and then we'll do one that has friction, and then it's time for the practice problems. Okay, so a new configuration. I have a 10 kilogram block, so it's heavier now, trying to slide down this ramp. And I have a 5 kilogram block that's trying to fall this way under gravity. And unfortunately, the two are tied together. So either this block's need to slide down the ramp is big enough to drag this one back upwards, or this one's need to fall down is strong enough to drag this one up the ramp. I don't know which one it is yet, so we'll have to do some numbers to figure it out. For this example, I'm going to skip friction just to keep it simple. We'll save friction for a few examples down the way. So I'm going to look at this thing, and I need to think about all the forces that are acting on this system. Well, there'll be a normal force because this is resting on the block, so that normal force is perpendicular to the surface. That means there needs to be some type of force opposing that normal force. And then there needs to be some sort of piece that's tending to slide the block down the ramp, and those two things together need to vector sum to the force of gravity that pulls straight down on that 10 kilogram block. This one's a little less complicated. It's simply experiencing a force of gravity headed downwards at mass times 9.8, which is 49 newtons. Okay. So in this little configuration then, force of gravity acting on this block, Fg, would be 10 times 9.8, which gives us 98 newtons. And that's headed this way. I end up with a piece that is perpendicular to the block, like so, F perp. And I end up with a piece like this, F parallel. Now, the perpendicular part, if you remember the sort of geometric magic that happened, if this is 50 degrees, then so is that corner up there. That's here. That puts the parallel component opposite to the 50 degrees, so I'm going to use sine. I have the perpendicular component adjacent to the 50 degrees, so I'm going to use cosine. That means that my perpendicular force should be the size of the full gravity cosine 50, and my parallel part should be the full gravity with a sine 50 attached. This is approximately 98. Cos 50 is 90 or 62.993 newtons, and this is approximately 75.072. All right. So I have broken this gravity into the piece that is perpendicular to the surface and the piece that is parallel to the surface. I've got the size of both those numbers. I've got the size of the gravity acting on this block here. So now I just need to start filling in forces and then find the net force. The only one I don't have yet is this normal force, but you can see that it is opposing the perpendicular part of the 10 kilogram block's gravity. That's here. So we've just have to lift this number and note that the normal force acting on the 10 kilogram block will be 62.993 newtons. As far as net force goes, F net this gravity pulling this way because of the rope, this gravity is going to be opposed by this force here, the parallel one. That's 75.072 newtons. So just looking at that, I can see that 75 is larger than 49. So that's the one that's going to win. I'm going to start with that force, 75.072 newtons. The only other force in line with that one is the 49 newtons there. And since it's pulling backwards, right, it's resisting this, not assisting it, I need a negative in there. And those things together should give me net mass times net acceleration. So 75.072 minus 49 is 26.072. The net mass of this system would be this mass plus this mass for a total of 15. So my net acceleration then would be 26.072 divided by 15, whatever that is. 26.072 divided by 15 gives me 1.738 meters per second squared. Okay. So this system would accelerate this way. So the 5 kilogram block is going to rise, the 10 kilogram block is going to slide down the ramp, and it's going to do it at that rate, getting faster and faster as it goes, until either the 10 kilogram block runs at a ramp or the 5 kilogram block runs at a rope. And since none of that information is labeled on there, like how far it has to travel, then we're done with this problem. We could add it in, and then it would just be a kinematics problem. But I think the point here really is to underscore splitting an inconvenient force into convenient components, and then using each of those pieces to identify all of the rest of the forces in order to get a net acceleration. Okay. I'm going to take the same example, but I'm going to take away the known angle, and what that's going to do is it's going to let me figure out the angle at which I could position this ramp so that these two things would be stuck. So I'm going to clear that off, and then we'll give that a try. Okay, so going through and filling in the information that's changed, this is still a 5 kilogram block, so its gravity is still 49 newtons. This is still a 10 kilogram block, so its gravity is still 98 newtons. What has changed is the proportion of that 98 newtons that is dedicated to perpendicular force and is dedicated to parallel force. So I'm going to have to leave this undefined for a minute, which means I can't write the normal force quite yet, because I don't know what alpha is. What I do know is that I'm trying to get this thing to be stuck. So that word there, stuck, that means that the net force is 0. There is neither a pull to the left nor a pull to the right, so that the acceleration ends up being 0. So if I were to try and calculate that, F net would normally be, I assume which one is going to win. And since this one won last time, I'm just going to assume that. So I need this force here, the parallel force. That is 98 sine alpha, whatever alpha is. That was a terrible alpha. There we go. So 98 sine alpha. And then I have this block hanging here, providing 49 newtons of force. And this block is still resisting this one's tendency to slide, so I'm going to put it in as a negative there. So to finish this off, I bring the 49 over, equals 98 sine alpha. Divide both sides by 98, I get 49 over 98 is sine alpha. That is 1/2. arc sine both sides. And I believe that's 30 degrees. Arc sine of 0.5. Yep, 30 degrees. Of course, anytime you arc sine, you have to use cast rule, this thing, to get your second angle. So one of them is 30 degrees. The second one would be 180 minus that, which is 150 degrees. If you flip this ramp 150 degrees, suddenly it's going to fall off. If you think about that, though, if this arm opened up to 150 and the block rolled around to the other side, I would have drawn this ramp, but reflected, and that's sort of the hidden stuff buried in this cast rule, right? Like if you take this machine and rotate it that way, its behavior doesn't change. Anyway, that is beside the point. What I just figured out is that if alpha is 30 degrees, this one is now strong enough to stop that slide. If I were to reduce this angle to less than 30 degrees, the proportion of gravity that's dedicated to the parallel component would be reduced. And at that point, any angle below this, the 5 kilogram is actually able to overpower the 10, which is kind of neat. So you've been able to find a thing that you can make toggle back and forth based on the angle that you set that ramp at, and you found the sort of tipping point between where one side wins or the other side wins. So I'm going to erase this, and I'm going to toss in some friction so you can see how that works. So I have a ramp here that is tipped at 20 degrees. There is an 8 kilogram block sitting on it, and there is a coefficient of static friction between the 8 kilogram block and the ramp of 0.3. So there's a few things you're going to have to remember here. The first one is that the force of gravity is mg, which for this block would be 8 times 9.8, which is 78.4, I think. Yep. Okay. From all of our other ramp stuff that we just did, we can split that into the parallel and the perpendicular parts. So the parallel piece will be this full gravity sine 20 degrees, which is approximately times sine 20 degrees gives me 26.814 newtons. And there is a perpendicular component, which would be the full gravity multiplied by a cosine of 20. 78.4 cosine 20 is approximately 73.672. Alright. And then you're going to have to remember the formula for the force of friction. Force of friction was the normal force acting on an object multiplied by the coefficient of static friction. It's usually written like this. So in order to figure out this friction, I'm going to have to figure out what the normal force is. Now, we used to just be able to park in force of gravity in the grade 11 course because everything was flat in grade 11. But now these things are tipped. So you have to remember that the normal force is pointing that way, which means it has to be opposed by the perpendicular piece of gravity. That's this here. So my force of friction will be mu 0.3 multiplied by the size of the normal force, which is this number here, 73.672, which gives me approximately 22.102 newtons. Okay, and of course we just figured out that the normal force was balanced by the perpendicular piece, which is 73.672 newtons. So I know the sizes of all the forces acting on that. I just have to worry about my net force then. So if I were to label these on here, I've got perpendicular piece going in. That's 73. I'm just going to use those digits because it keeps the diagram simple. A normal force that is 73, those two things balance each other. I have a parallel force going this way of 26.814, sorry. I have a force of friction that is resisting that slide, because friction always resists your slide, of 22.102. So this net force calculation is going to look very similar to what we had when there was a block hanging there. It's just a force that's dragging back on you. So net force then, if I look, it appears to me that this 26 Newton force is going to beat that 22 one, so on it goes first, 26.814 and a 22.102. This one is resisting the motion, so it becomes negative. That should give me my net mass multiplied by my net acceleration. All right, so 26.814 minus 22.102 should be 4.712. Net mass is 8 kilograms. So 4.712 divided by 8 should give me my net acceleration. Let me just check that. Well, good, I can still subtract in my old age. 0.589 meters per second squared. Lovely. So it turned out the friction, whatever materials these are made of, having a coefficient of friction of 0.3 between them, was insufficient to keep that block stuck on the ramp, which means it will continue to slide downwards and it will accelerate as it goes at that particular rate. So this begs the question then, what if I took out that specific angle and I wanted to find how steep I could tip this thing so that that block was stuck? So I'm going to erase this, I'm going to get rid of the 20, just like I did before, and we're going to make this an unknown angle and see what happens. Okay, so going through the work that we had before, this is still an 8 kilogram block, so this is still 78.4 newtons worth of gravity. When I break it into parallel and perpendicular, it's still sine and cos attached to that full gravity, but it's of an undetermined angle. I'm going to have an alpha there instead of a number, which means I can't do my normal force because I don't have a number here yet, and I can't do my friction because I don't have a number here yet. But what I could write is that that force of friction is going to be the coefficient, 0.3, multiplied by the normal force, which happens to be the perpendicular force, which happens to be 78.4 cos alpha. Now, I could multiply those two together. I'm not going to because it's going to illustrate something for us in a moment. So I don't have any numbers. So if I don't have numbers, then I can't get an acceleration. And that should make sense because the acceleration depends on how steep you make that ramp. But if I change the question to say, what angle would make it stuck? Now I'm trying to do a net force of 0, right? Neither pull down the ramp nor up the ramp. So I have to pick one, assuming it's going to win. So I'm going to assume this one just because that's what we've been going with. That is the parallel component that's here, 78.4 sine alpha. And then I have the force that is resisting it. That's this friction, which I've deduced here. 0.3 times 78.4 cos alpha. And this force is resisting that one, so it needs to have a negative on it. So to solve this, I'm going to take this piece, I'm going to throw it to the other side. So I will have 0.3 times 78.4 cos alpha equals 78.4 sine alpha. And interestingly, there's a multiply by 78.4 on this side and a multiply by 78.4 on that side, so I can just divide them out. So I'm left with 0.3 cos alpha equals sine alpha. Now that is problematic because you don't have an antifunction that can undo sine and cos. You've heard me hear this before in the projectile motion videos. And the solution to the projectile motion problem was to use a trig identity. So we're going to do the same thing here. We're going to have to remember that sine divided by cos is the same as tan. So I'm going to bring this over here. And I'm going to spot that that is the same thing as tan alpha. And so alpha would be arctan of 0.3. So arctan of 0.3 is 16.699 degrees. So if alpha is less than 16.699 degrees, then the friction component is bigger than the slide component. So this thing won't move. And if you think about that, like that's how ramps work, right? You can put an object on your table, you can put a textbook on it, and you can lift the feet a little bit, and it won't go anywhere. You can lift them a little more, and it won't go anywhere. And there's a critical angle, this number here, at which once you tip the table beyond that angle, the book starts to slide, or your dinner, whatever you've carelessly left on the table you're trying to flip. So you can calculate the sticking angle, right? Like the maximum steepness you can make this ramp before thing slides using this trig identity. And if I were to try and be even a little more general, if I didn't use a specific number, so that's the 0.3. If I track that through, that happened here, it mattered here. Where did it matter? It mattered there. It mattered here, and here, and here, and here. Well, you've got a relationship right there. The maximum angle that you can tip that ramp before things start to slide depends entirely on the coefficient of friction. And you notice up here, the thing that had the mass in it, or the force of gravity, it ended up dividing out. So it doesn't matter if this block is 8 kilograms, or 80 kilograms, or 8,000 kilograms. If you tip it beyond that angle, friction is insufficient to hold it in place. All right, so I'm going to go through and I'm going to try one of these with a hanging block and a sliding block with friction, and we'll see how that goes. Okay, so there's a bunch of work to do here. First off, I'm going to start with this 15 kilogram block because it's pretty straightforward. It has some gravity pulling it that way, which will be its mass multiplied by 9.8. 9849 is 147, I think. 15 times 9.8 is 147 newtons. Okay. Next gravity I'm going to do is on this 10 kilogram block. Would be its mass times 9.8, which gives us 98 newtons. But that block is on a non-flat surface, so I'm going to have to break that force into a component that is parallel to the surface and a component that is perpendicular. So the parallel part will be the full gravitational force, 98, multiplied by the sine of 30 degrees. And in my head, I'm checking the parallel part should go to 0 if this angle is 0, and that's what sine does. Sine 30 is 0.5, I believe, so I should get 49 as my answer. 98 sine 30, yep, 49 newtons. There will also be a perpendicular piece to this gravitational force, which will be 98 cosine of 30. Cosine 30 is root 3 over 2. I can't do that times 98 in my head. 84.870 newtons. So I've got my parallel piece, which is 49, and I have my perpendicular piece, which is 84.87. Immediately after that, I can identify the normal force. The normal force has to be strong enough to counter this, otherwise the 10 kilogram block would crush its way through the wedge. So the normal force has to equal the perpendicular force, which happens to be 84.870 newtons. And once I have a normal force, I can calculate friction, because friction is the coefficient of friction multiplied by how hard those objects are pressed together. Coefficient of friction in this case is 0.8. The normal force is 84.870 for a total of 67.896. All right. So I'm going to start looking at all of my forces, and I'm going to try and find the biggest one. I have a 67 here. Well, that's bigger. That's the same. Smaller. That's bigger. There it is. There's the biggest one. So if this thing moves, the 15 kilogram block must be dropping, and this 10 kilogram block must be sliding up the ramp. That's the only way it will work, because that's the biggest force. So I'm going to set this up as a net force calculation. F net is this 147. So check. But it is being opposed by a tendency of the 10 kilogram block to slide down the ramp. So that's 49 in opposition. That's this one. But I've also got friction from this 10 kilogram block. That's here. That is also in opposition. So you notice that I've never put a formula up there and written in FG minus FF. I haven't done that because that will shoot you in the foot. What's better is to identify your biggest force and then subtract anything that's resisting it and add in anything that's helping it. We haven't had an example of something helping yet. That may come later. So that together should end up giving me M net, A net. So I need to take my 147 subtract 49 and subtract 67.896, which gives me 30.104 newtons. Net mass of this system would be 10 and 15 is 25 kilograms total. So my net acceleration should be 30.104 divided by 25. Which gives me 1.204 meters per second squared. Right. Whew. So after all that work, I've decided that based on this drawing, this 15 kilogram object is heavy enough to stop this 10 kilogram block from sliding down the ramp. And not only is it capable of stopping it, it's capable of reversing its direction, dragging it up the hill, despite the fact that even friction is fighting against that action, for a net acceleration in the system of 1.204 meters per second squared. So there's a couple of these to practice in the problem sets where you're going to have to break up a gravity. You might have to solve an angle at a sticking point. You might have to solve an angle for a hanging block and a sticking block to not slide. You're just solving for different variables, but the setup is always the same. So I'll give you some time to try those. Good luck.